Yeah, so once we have an orthogonal basis S, then by normalizing each vector, we get an orthonormal basis S prime. And from the theorem we looked at, every element U in V can be written as this linear combination here. And I was explaining how we come up with this step here. You see, this is inner product of U V1. Then divide by V1 times this V1, uh, get we get V1 squared, then times the V1. Then we take this, this, we take this inside, this becomes V squared, then so on. So inner V, U V1, U2, V2, and so on. So we are here, so we get this. This is what we get. Next, we want to look at another theorem. This theorem is telling us that if V1, if a set S is an orthogonal set of non-zero vectors in an inner product space, then that set is linearly independent. So that set is linearly independent. What does linear independence mean? When we write this set as a linear combination of the basis elements, then the only way that linear combination can be zero is if each of the constants is equal to zero. So to prove that S is linearly independent, we need to show that each of the constants is zero. And we can write, when we take the inner product, this linear combination with VI, that one should give us zero, then VI, because if this set is linearly independent, then the entire this is going to give us a zero. And we know from properties of inner product space that once we have a zero here, then the result becomes a zero. So it implies that when we have K1 inner product V1, VI plus K2, and so on and so forth, this will be a zero because this one comes from that. And since VI, Vj is equal to zero for this different from that, because this is coming from the fact that S is orthogonal. So it means each pair of distinct vectors is orthogonal. So we get this relation. And so it follows that this one will also be zero. And hence S, because so it means if all the k's are equal to zero, then it means S is a linear independent set. Next, we look at the projection theorem. If you have a question, feel free to raise the hand. Or unmute and talk. I'll attend to you. So we want to look at the projection theorem. Next, we want to talk about the projection theorem. We want to talk about the projection theorem. So if W is a finite dimensional subspace of an inner product space V, then every vector U can uniquely be expressed as W1 plus W2. W is a subspace of the inner product space V. Then where W1 is in W and W2 is in W with this sign. We said this is the orthogonal complement of W. So we said once we have an inner product space, this projection theorem is actually telling us that every vector in U has two components. It has a component which is orthogonal to every vector in V. Therefore, it belongs to the to W. It belongs to W. And then it has the other component which is not orthogonal, so it belongs to the orthogonal complement. Hello. How are you? Mm. Oh. Members, sorry, I was attending some call here. Sorry about that. But we are back to the projection theorem. So the projection theorem is basically telling us that every vector u in V has two components. It has W1, which belongs to the subspace W, and then this subspace W is it is a space of all vectors which are orthogonal to other vectors in V. In other words, it is the subspace of the orthogonal vector. So not if we have a vector space, then it means we can pick vectors which are orthogonal. We put them in some W, so it will be a subspace of V, and then others which are not orthogonal, put them in the orthogonal complement. So the projection theorem tells us that every vector U in V has two components. It has a component which is orthogonal to every other vector in V, which belongs to the orthogonal, which belongs to W, and has the other part which is not, which belongs to the orthogonal complement. So the vector W in W1 W in the theorem above is called the orthogonal projection of U to W, and is denoted by the projection of U on W. It is denoted by this. And the vector W2, which is in the orthogonal complement, is called the component of U orthogonal to W, and is denoted by that. Okay, so W1 is called the orthogonal projection of U onto W, is this, and W2 is the component of U that is orthogonal to W. Yeah, this is the component of U orthogonal to W, and is denoted by this projection. So this means from the projection theorem that U is equal to this guy here plus this guy. And it follows from the projection theorem that every vector U can be, this is the W1, which is the component, which is the projection of U on W, plus the component of U, which is orthogonal to W. So we get this. That means that to get the component of U, which is orthogonal to W, we get the vector U minus the orthogonal projection of U on W. So we are here. I hope are together. If you get a question, feel free to ask. Next, we talk about an example if you have no queries. No, there's another theorem. This theorem is telling us that if W is a finite dimensional subspace of an inner product space V, then the vectors V1 up to VR is an orthonormal basis for W. Is an orthonormal basis for W. Okay, if if we pick W is a finite dimensional subspace of an inner product space V. If we have an orthonormal basis for that subspace and U is any vector in V, then the projection of U on W can be computed from the inner product of U V1, inner product of times V1 plus inner product of U V2 times V2, and so on up to VR, whereby this is the basis for the subspace. And next, if this is a basis, if this is orthonormal basis for the subspace, then we see, of course, Roman 2 is following from Roman 1 because this inner product can be looked at as, you know, we can if this is orthonormal basis, because each vector can be orthonormal. Okay, in Roman 1, I think this word is supposed to be orthogonal, then Roman 2 is orthonormal. So if it is orthonormal, then it means we are normalizing each vector V1 up to VR, and so we can get this linear combination here. So this theorem is telling us how we can compute the component of U that is orthogonal to W, and the projection of U on W, whereby W is a subspace of the inner product space V. Okay, example, our inner product space is R3, and the inner product defined on it is the Euclidean inner product, and W is a subspace which is spanned by orthonormal vectors V1 and V2. So V1 and V2 are orthonormal vectors. So we want to find the projection of U, which is this, on W. We want to find the projection of U on W. And then we also want to find the component of U that is orthogonal to W. In other words, in this example, we want to compute this guy, and then after that, we'll compute this guy. So we'll be using that. Okay, so solution. Since this is an orthonormal basis, it means that the projection of U on W can be written as this linear combination. We have two basis elements, so it is the inner product of U V1 times V1 plus inner product of U2 V2 times V2, and this is equal to we take the dot product, we can, when we take the dot product of U V1, it is 1 times vector space V1. The dot product of U V2, it is negative 1/5 times vector V2, which is this. So when we do this addition, you see this is going to be 0 plus 4/5. So it gives us 4/5. This is 1 plus 0. So it gives us 1. This is 0 minus 3/25. So we get this. So it means this guy here is the projection of U onto W. We can come back here and see that the inner product of U V1, this is 0 plus 1 plus 0. Inner product of U V2, this is minus 4/5 plus 0 plus 3/5. So that one gives us negative 1/5. So we get this. So this is the orthogonal projection of U onto W is given by this vector. Part B, we want to find the component of U that is orthogonal to W. From what we saw, it is that component is this guy here, and is U minus the orthogonal projection of U onto W. But U is this, and the orthogonal projection is that. So that one gives us 21/25, 0, 28/25. So what we are saying here is that from the theorem, we saw that every vector in V has two components. It has a component W1, which is the orthogonal projection of U onto W. It also has a component W2, which is the component of U that is orthogonal to W. That means that U can be written as the sum of its orthogonal projection plus its component, which is orthogonal to W, which belongs to that. So we use that to get this. Questions?
Excuse me, sir.
Questions?
Excuse me, sir. On part A.
Who is talking? James.
On part A.
James, can you speak louder, James? James, speak louder. Increase your volume.
So maybe someone else, but it's not James.
Is someone else?
On the
Someone is talking, but They are talking slowly. I can't hear you.
In this example, on part A,
That is Semaganda. Semaganda, try to increase your volume, please.
yes,
Mm,
on part A,
yes.
that figure is not over 5, it is 4 over 25.
Which figure? This one.
Because yeah.
Okay, this is 0, 4. Okay, yeah, thank you. Thank you. This guy here is 25. Is 4 over 25. Members, have you taken note of that?
Yes.
Okay, this is 25 here. Okay, any other question? Are we together? Can we proceed? Okay. Um, next is a simple exercise which is related to the example we've done above. So you can take time and do it. Okay. The last part of this lecture, we want to talk about the Gram Summit orthogonalization process. This is the last part of the lecture. We start with the theorem. The theorem tells us that every non-zero finite dimensional inner product space has an orthonormal basis. Every non-zero, so every inner product space, this theorem is telling us that every inner product space has an orthonormal basis. So we want to prove that theorem. We let V be any non-zero finite dimensional inner product space. Next, we suppose that this is any basis for V, because first of all, if it is an inner product space, then it must be a vector space, and every vector space has a basis. Yeah, if it has no basis, at least it has one basis, which we call its usual, or its norm, or its Euclidean basis. So the theorem is telling us that every inner product space has an orthonormal basis, and to check it, we let V be any inner product space, and then we let U1, U2 be any basis for V. Now, to show that, to prove this theorem, it is enough to show that V has an orthogonal basis. For us to show that V has an orthonormal basis, it is enough to show that it has an orthogonal basis, because once we have an orthogonal basis, then we can change it into, we can normalize each vector and then to become an orthonormal basis. So, and so that means that the rest of the work is to change any basis V into an orthogonal basis. So we are going into the process of changing the basis V into an orthogonal basis. And that process is what we call the Gram Summit orthogonalization process. These are names of the mathematicians who discovered or who invented this theorem first. Okay, so it follows the following steps will produce an ortho. The following steps will produce an orthogonal basis. The first step, we let the first element V1 of the orthogonal of the orthogonal basis be U1. U1 is any vector. Then step 2, we obtain the vector U2, which is we obtain V2, which is orthogonal to V1 by computing the component of U2, which is orthogonal to the subspace W1 spanned by V1. And how do we compute it? V2, we let V2 be the U2 minus the space, the orthogonal projection of U2 on W1. But we know that the orthogonal projection of U2 on W1 is given by this guy here. So we get this. So that means we have V2. So we have V2 now. If V2 is 0, then it means V2 is not a basis. is not a basis vector, because in a basis we have non-zero vectors. But this is not possible because U1 and U2 are basis vectors, and hence they are linearly independent. So when we have U1 and U2 being linearly independent, it means this cannot be, V2 cannot be a zero vector. So we are doing the process of changing any vector, any basis S, which is U1, U2 up to UN, into an orthogonal basis. So the first element of the orthogonal basis is V1, which is the first element of that any vector. The second element is got by computing the component of U2, because we have U2 the other side, so we compute its component, which is orthogonal to the space W, and then that one gives us the second element. The third element, V3, uh, uh, that is orthogonal to V1. That is orthogonal to V1. That is orthogonal to both V1 and V2, because now we have V1 and V2. V2 should be orthogonal to V1. V3 should be orthogonal to both V1 and V2. And to compute this, we compute the component of U3, which is orthogonal to the space W2 spanned by both V1 and V2. So it means that V3 is going to be U3 minus the projection of U3 on U2 on W2, whereby W2 is the space spanned by V1 and V3. So the projection of U3, we know that that projection is from the theorem we looked at. It is going to be the span. Okay, it is V1, V2, so it is U3, V1 over this norm, times V1, then plus this over that times V2. So this is how we compute the projection here. So that means V3 is going to be U3 minus this projection, which is given by that. And when we continue the process, when we continue this process, we get UN, which is UN minus this, and so on up to N minus 1, because U3 we stopped at V2. U2 is stopped at V1. So UN we stop at UN minus 1. Now these vectors V1, V2, V3 up to Vn will form an orthogonal basis. And once we have an orthogonal basis, then normalizing each vector in the orthogonal basis, we get an orthonormal basis. Hence the theorem that every inner product space, every finite dimensional inner product space has an orthonormal basis. And the preceding step-by-step construction for converting an arbitrary basis into an orthogonal basis is what we call the Gram-Summit orthogonalization process. Okay, if there are no questions, I can take you through an example, and that will mark the end of the lecture. Remember, we have 7 minutes to the second break. So if the 7 minutes elapse before we complete the lecture, then I can reschedule. And we can take a 2 minutes break, then we come back for the last the last lap of the lecture.
Excuse me, sir.
Yes, please.
Am I the only one without these notes? I'm not having them.
You're not the
Of this
only
last Gram Summit.
You're not the only one. This last part of the Gram Summit orthogonalization process, I haven't uploaded it.
Okay.
Yeah, but I'll do the needful. There is some other remaining part of this chapter that I need to first type, and then when it is done, I will upload it. Yeah, and I will also upload these very slides. These slides will be uploaded as soon as possible. Then the notes will come after that last part has been worked on. Is that okay?
Right.
Yeah. Any other
Yes.
query? Can we go to the example? Okay, so I think the example can even explain far much better than the theorem. So in this example, we let V be a vector space of polynomials of degree less or equal to 3. And we define the inner product on that vector space as the inner product. When we take the inner product of two polynomials f and g, it means we take the integral from -1 up to 1 of the product with respect to t. So we want to apply the grand summit process for this for this basis of v. Process for this basis of v. So in other words, we want to find an orthonormal basis. We want to find an orthonormal basis for this P3. So the standard basis for P3 is S, which is 1, then t squared and t cubed. Remember, every element in V is a polynomial of degree less or equal to 3. So that means any polynomial of degree less or equal to 3 can be written as this. This is the standard basis for polynomials. I hope you remember this from linear algebra 1. Now we perform the grand summit orthogonalization process to change this standard basis into an orthonormal basis. So the process, we let f naught, the f naught is 1. We let f naught be 1. Then we compute f2 by computing the component of t that is orthogonal to the space w, which is spanned by f1. So that component is t minus the inner product of t 1, then divide by the inner product of 1, 1. This is the same as the norm 1 squared, then times the first element, which is 1. And the inner product of T11, it is going to give us, it will give us a 0. Why does it give us a 0? Because from the definition, we integrate inner product of T. If we have T here and 1 here, then it is integral from -1 up to 1 of T dt. And when we do that integral, we get T squared over 2. From 1, when we put in 1, we get a half. Minus when we put in -1, we get a half. So a half minus a half, we get 0. So the inner product here is 0. That means this component is going to be 0. And so f1 becomes t minus 0, which is t. Okay, so we find f2. We find f2. F2 is got by computing the component of U1. This is U0. We find the component of U1, which is orthogonal to a space W2, which is spanned by F1 and F0. So that is the T squared minus the inner product of T squared, T1, divided by this one, then times 1, which is this for F0, inner product T2, T2, divided by inner product of T1, I mean of T, T, then times Z, the F1, which is T, and that one gives us the T squared, then the inner product of T squared, 1. It gives us 2 over 3. How do we get 2 over 3? This is the integral from -1 up to 1 of t squared, which is t cubed over 3. When t is 1, we get a third. then minus. When t is -1, we get -1/3. So a third minus a third, we get 2/3, which is this. 10 times 1, we are here. The inner product here is going to be 0 because it will be integral of t squared times t, which is integral of t cubed, which is t to the power 4/4, and that one gives us a 0, then times t. So we get f2 as t squared minus a half. Next, we want to find f3, which is the end. Remember, so we found f0, f1, f2. Next, we want to find f3. So to get f3, sorry, this is still the solution. So f3, we get, compute the component of u2 that is orthogonal to f2, f1, and f0. So that is going to be t cubed minus, this is t cubed, 1 divided by 1 times 1. T squared t divided by this times t. Then t cubed, and so this is this, minus that. Then this gives us what? So we have